All right, everybody. So the good news right here is that what we're doing at the beginning of Chapter 6 really isn't going to feel very different at all from what we were doing early on in Chapter 5. What were we focused on early on in Chapter 5? What concept? Area under a curve. Now we're going to be just a little bit more specific with that, and you can tell from the title already. In the first chapter 5, guys, we were working on problems like this. So we had a generic curve, we had two limits of integration that we were just calling A and B, and we were just interested in trying to find the area underneath that curve on the top, but bordered by what on the bottom for every single problem that we did. Yeah, every single one went from curve to x-axis, or occasionally they were below, so they went from x-axis down to the curve, but that was the important idea, and A and B were the limits of integration. So just to kind of review something that we did, okay, early on in Chapter 5, we found our approximation here by cutting this region up into rectangles. How many? Well, that's the right answer. That's good. And we started off with n being a relatively small number. Didn't we do a lot of like 4s right at the beginning and maybe even some 3s? Because it was a small number and we were able to deal with it and it wasn't too bad. And eventually we increased the value of n, and we needed what tool in order to do that efficiently? Sigmas. Relax. Nobody's going back to sigmas today, but I'm just trying to get you to remember what we did 5-6 weeks ago. So what we did, let's just draw one of these guys. We drew a rectangle here, and depending on what type of rectangle we were trying to draw, it looked like a few different things. But for that green rectangle right over there, if we wanted to find the area of it, we had a couple things to consider. Right here, guys, the height of each one of those rectangles we denoted simply and generically as what? A little more specific than h. Whoa, that's the next one down. F of x, everybody, it essentially is what your integrand ended up being right there. So f of x was the height of our rectangles right there. Now, how about the width of each one of those rectangles? We initially started calling that delta x. And do you guys remember that formula of b minus a over n, and that's how we got delta x sometimes? So again, delta x started off that way, but eventually, if you guys remember the notational change, the delta x eventually became, the Greek delta became the Roman d, and that's where the dx at the end of our integrals came from. So when it came time to do the width of a rectangle, everybody, that's what the dx stood for. It was kind of an evolution from the delta x that we had earlier. And so with that in mind, everybody, if we went down to this third line right here and said, okay, let's talk about the area of the entire shaded region, I probably should have put a line in between right here. What's the area of one rectangle, everybody, if this is its height and that's its width? Okay, f of x is the height of each rectangle. Now guys, if you're writing this, humor me for a second. Write your f of x and then leave some room here, okay? And then we're going to put a dx at the end of all that. So that quick little expression right there, f of x times dx, got us the area of one rectangle. And then we would find the areas of all of them and add them up. And eventually, as we got better at this, we let that n value get higher. We did a couple of n equals 10s, and I don't remember if we did a 12, but I think in one homework problem we did like a 20 or 100 or whatever. But the big point is this, guys. What did we learn? If we wanted our estimates to be as accurate as possible, we wanted n to be as big as possible, and what would be the ideal number of rectangles to cut down on the error margin? Okay, infinity. Now there was a problem with that, we knew. The other trade-off though to talk about though is that as your number of rectangles approached infinity, what did that do right here, guys, to the width of each rectangle? It made that approach 0. So it was cumbersome, but if you remember at the very beginning of 5.2 when we were talking about Riemann sums, we did a summation starting at like k equals 1 and ending at n. And then what did we stick in front of that sigma? A limit as n approached infinity. So it got difficult just to write, let alone to actually compute. A limit, you don't need to write this down, guys, but eventually we were doing a limit as n approached infinity of the summation here from k equals 1 up to n, and then it was basically f of x times dx. And we talked about how over the years there was just a notational change right here, and all of this mess here, guys, the sigma, but including the limit, got replaced by what really nice symbol? That's the integral sign. A Roman S took the place of sigma, which was the Greek S. So I think that hopefully made a little bit of sense when we saw it. So back to right here, guys, for the area of the entire shaded region, we would put an integral in front of this, and we eventually learned just to use A and B as our limits of integration. So everything we have here in red, guys, I'm hoping seems familiar. We just took a test on this. Oh yeah, that's what we were working on in Chapter 5. Now things are changing ever so slightly. Now, as I think you guys can tell from the title, instead of only looking at a region that's bound by a curve on one side and the x-axis on the other, what are we going to throw into the mix right now? A second curve that could be located above or below, but I think with the way we've set this one up, I'm going to go ahead and put this curve below. So what I'm going to do, guys, and it makes no difference at all what your curve looks like, but I'm going to draw another one underneath right there, and I'm going to call that y equals, how about g of x? Okay, and now, guys, instead of just stopping this thing at the x-axis, we're going to let it go all the way down, in this case, through the x-axis until it reaches that second curve. So let me get rid of my A right here and my B right here and just write them a little bit differently. So this A value right there goes all the way down, and this B value goes all the way down as well. And now we're looking for the area of this entire region here, everybody, which is going to look like this. So we're going here, 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 and there. So we're looking for the area of that entire yellow region now that doesn't just stop at the x-axis the way it did back in Chapter 5. So what's going to happen? My green rectangle, guys, is now going to extend downward as well and now start to look something like this. And let's talk then about how that changes the three things that we wrote down on the bottom of this slide. Is the height of your rectangle still f of x? No. Do we think we know what it is? F of x plus g of x? Or minus? Plus? Okay, now what I have drawn right here, guys, is only one of three possible cases. But in this case right here, guys, doesn't it look like this y value right up here is positive? Pick a number, Josh. Sure, it's 8 units up. It sure looks like this y value right here is negative. Now, is it theoretically possible this y value on the bottom could be negative 8? Okay, I'm doing that for a reason. Now, I want you guys to think about what you just said, because one of those answers was right and one of them is wrong. Is it going to be f of x plus g of x or f of x minus g of x to get you the height of this rectangle? What happens if you add 8 and negative 8? Are you telling me the height of that green rectangle is 0? Pretty clearly it's not. The way we measure height, everybody, is we're going to do top value minus the bottom value. And in a case like this, the 8 minus the negative 8 would tell you that height is 16. Now, would that work if both numbers were positive? If it went from 8 to 2, top minus bottom would be 6. Does that seem right to you guys that the height of that rectangle would be 6? And what if it went from negative to negative, like from negative 1 to negative 10? Negative 1 minus a negative 10 would be 9. Wouldn't that be the height of that rectangle then? Okay, so that's it, guys. So what's going on now? We got to change this just a little bit. Our height of our rectangle is going to be f of x minus g of x, all right? So that's what goes there for the height of every one of these rectangles. And it works in all three cases. If they're both positive, if they're both negative, or one of each. You guys might want to write yourself a little note here. What we really just did, what we always do, is top value minus the bottom value. So let's keep that in mind. Is the width of the rectangle changing, you guys, or is that still dx? That hasn't changed at all. So if we understand those two things, we should now know that the area of our shaded region is only going to change in what little way? Yeah, in the integrand, the height of the rectangle is now going to be f of x minus g of x. Okay? Now, I said this to you back in chapter 5. Let me say it again here. You will hardly ever see that dot right there. Nobody writes it that way. Conventionally, we don't have to do it, but I think that conceptually, it helps us to understand that just like before, we're multiplying a height, f of x minus g of x, times a width, which is the dx at the end. Really, guys, wouldn't it probably be appropriate to do this? Otherwise, it kind of looks like, without it, it kind of looks like the dx is only getting multiplied by g of x. That said, nobody ever does that. We talked about this in 5.2. The dx at the end and the integral sign at the beginning kind of take the place of a set of parentheses, and everything in between those two things is understood to be your integrand. So guys, this is not like earth-shattering right here, but this is the big takeaway for this section here in 6.1. That if we want to find the area of a shaded region bounded by two curves, f of x minus g of x, the only thing different from what we did in chapter 5 is we now have a minus g of x at the end there. In a manner of speaking, this is what we've been doing. Every region in chapter 5 had what for its lower boundary? The x-axis, which is the function, right, y equals 0. So really, the g of x right here was 0 in everything we did before, and is there any point in writing a minus 0? But you could have gone back and looked at every problem you did in chapter 5 and put a minus 0 there. And, oh, it's really what we were doing. Okay? So let's see it in action, guys. What time are we out of here today? Oh my God, I got like 7 minutes. Let's see what we got. Find an area in between. We've got a linear function and we've got a constant function. And the reason I started you with this is it's pretty easy and we can check it with geometry. But what you guys are going to want to do at the beginning of just about every problem that we're going to do is draw your region out. So 1/2 x plus 4. We're going up 1, 2, 3, 4 units, everybody. Y-intercept of 4. And a slope of 1/2 is going to look something like that. And a constant function of y equals -2 is, of course, going to get us a horizontal line right over here. Okay? And we want to know what happens from x equals 0 to x equals 8. Well, 0 is easy enough. That's going to get us this red segment right over here. And 8, I don't really care to count, everybody. I'm just going to randomly go out there, shoot this guy up, this one down. And does everybody see the region that we're looking at here? There, there, and there, and there. Okay? Hey! A linear function and a constant function and then two vertical lines, it formed what shape, everybody? It's a trapezoid. So let's do this one geometrically. Hey, we just got done doing this, everybody, in chapter 5. Area of a trapezoid is 1/2 times height. What's our height here, everybody? Horizontally now, the distance between your bases, your height from 0 to 8 is 8, and now we need the sums of the two bases. So this base right over here, hey, let's test out our little method. What's this y-coordinate here, everybody? 4. This y-coordinate right here? -2. Top minus bottom? 6. So 6 is the length of your first base. And then how about over here? How about this y-coordinate, guys? When x is 8, what's the value of this function here? 1/2 of 8 plus 4, yeah, is 8. That's correct. Obviously, this one is still -2. So 8 minus -2, that gets us 10 over here for the measure of the second base. So let's put all that together. We don't have to think too hard about this. 1/2 of 8 is 4. 6 plus 10 is 16. 4 times 16? Okay, so 64 square units is the answer we got geometrically. If our calculus method is worth anything at all, we better get what answer? 64. So let's try it and see what we can do, everybody. All right, here we go. Area is going to equal a definite integral, starting where? 0 and ending at 8. Our integrand, everybody, is f of x minus g of x. Top function minus bottom function. So what is the top function, everybody? It's y equals 1/2 x plus 4. So there's your top function. Not a terrible idea to put that in parentheses. Minus the bottom function, which is y equals -2. Close that off, and the width of each rectangle is dx. Okay, let's see if we can't clean that up just a little bit. So area is the integral from 0 to 8 of a 1/2 x plus 6, taken with respect to x. And this certainly doesn't look like something we need a calculator for. Let's see what we got. Integral of a 1/2 x, everybody. The x becomes x squared. We divide the 1/2 by that new exponent of 2 to get a 1/4 plus a 6x, and at the end of this mess, plus c's for indefinite integrals here. For a definite, we put the bar and we evaluate this thing from 0 to 8. So here you go, guys. Let's try some brackets here. 8 squared, 64, and 1/4 of 64 is 16, plus 6 times 8, 48, and that's that, minus, now let's not assume what happens when you put a 0 in here for both of your x's. Yeah, okay, you end up with a 0 right there, and that gets us a final answer, everybody, of area equals 64. And since it was an area question, isn't that what it said? Find the area between. I'm going to include units right here, so 64 square units, and that's what we get. So hey, did our calculus and our geometry answers agree? All right. Does that make us feel pretty decent about the calculus method that we just came up with? But we weren't really expecting that not to work, right? Well, you guys pack it up. We got time for one more problem here. Come on, we can do it. All right. Questions on that or not too bad? Nah, not too shabby. Let's do this one too, guys. We're going to find the area in between a cosine wave and a sine wave. But of course, the weird thing about that is if you were to draw these out, how many times do they intersect? Infinitely many. So we had to limit the domain right here, or the interval, just to be between 0 and pi over 4. The other tricky thing here is this. Which one of these functions is on top? Don't they just intersect a ton? Like infinitely many times? So one's on top and then the other one's on top a little bit later on, so graphing this is really a good idea. Now lucky for us, we don't have to graph this very far. We know we're never getting higher than 1 or lower than -1. Our sine wave starts at the origin, everybody, and it shoots up to a peak and then comes back down. Where is that first peak? At pi over 2. That's already farther than we needed to go here, guys. We only want to know what's going on up to pi over 4, so we'll go with that. And our cosine wave starts at 1. At pi over 2, cosine is now down to 0, so this graph is going to look something like that, and that's as much as we need. So if I go back to highlighting, and you guys are going to do a lot of shading right here, we're doing this. We're doing that, which always makes a straight curve right there. I hate that. All right, so we're looking at that region right over there. And let's see what we can do in 2 minutes, everybody. Okay, let's get to it here. Area equals a definite integral starting at what x value? 0. Ending at pi over 4. And now our integrand is always top minus bottom. So be careful now. For this particular interval, which function's on top? Cosine, but can we see further down how sine is above it? So it depends where you're looking right here. But this one is going to be cosine of x on top minus the sine of x on bottom, and dx is going to be the width of each one of our rectangles. Okay, so let's see what we can do here. Area is going to be antiderivative of cosine, sine of x, because the derivative of sine is cosine. Antiderivative of a minus sine of x, plus cosine of x. So it's sine of x plus cosine of x from 0 to pi over 4. All right, and let's see what we got. Plugging in the pi over 4 first. Sine of pi over 4, root 2 over 2, plus the cosine of pi over 4. Oh, same thing, root 2 over 2. Now this is a great example, guys, of why you don't just assume that 0 as an input gets you 0 as an output. You got to think about it, especially with trig. Sine of 0, that's 0, but the cosine of 0 is 1. So putting this together, there's not much you can do, but root 2 over 2 plus root 2 over 2 2 root 2 over 2. And what happens there? The 2's cancel and you just end up with a root 2 minus 1, and you can't do anything to clean that up, everybody, and that is our answer. Now, in the 10 seconds I have left, is it realistic? Let's go back and look at the yellow region. What does it most closely mimic geometrically? A triangle, right? Hey, everybody, what's the base of this triangle right here? 1. How about the height? That's pi over 4. So the area of that triangle would be 1/2 times 1 times pi over 4, which would be pi over 8. Now pi's about 3, right? So the answer is about 3/8 or 375. Anybody know what root 2 is as a decimal? 1.414. Minus 1 would get you about 0.4. So is that 0.4 fairly close to that 3/8 right there? It's close enough. All right, get out of here. See you guys tomorrow. I almost said have a good weekend. Today's Thursday. All right. Right, not quite. All right, see you, everybody.